the PowerPoint. And nope, I have to share it. God bless me. God bless everybody. God, it's whoever blesses, do the blessing. Okay. And that was it for epithelial tissue and glands. And now we're going to get into connective tissue. Ooh, the second type, or primary tissue type. The first primary tissue type was epithelial tissue, including all the glands. And we talked about simplified and stratified, and it was squamous and cuboidal and columnar, and then you had pseudostratified columnar, and then you had transitional epithelium. Yes, all that existed. Now we have connective tissue, which is a whole nother shebang. It is found everywhere in the body, but depending on where it is found, its amount varies greatly. And it's the most abundant and widely distributed of the tissues because it includes things that you probably don't think about as tissue. So it is connective tissue, which is the proper connective tissue that's underlying the skin and in between your joints, and it has something to do with the elasticity of the skin and whether you have wrinkles or not. If you have stretch marks, it's because you have less collagen than others, and stretch marks are totally normal. And you know, it's in your ear. This is elastic cartilage tissue. It's everywhere. And you have dense and loose, and we'll see pictures of what that looks like. Cartilage itself, which is a very hard material, like your nose here, the very tip of your nose is cartilage, the bony part that's not actually bone, it's cartilage. The very tip of your sternum, your whole skeleton as a fetus in the uterus is cartilage that eventually hardens over time. Some of it hardens before you are born, and some of it hardens after you're born. Bone is a type of connective tissue, and then so is also blood. Blood is a tissue. So these are our main groups of tissue. The major functions vary depending on what the tissue is doing. So you have binding, like the basal lamina and connective tissue under our skin. You have support for bone and cartilage. Protection, bone, cartilage, and fat. Fat is also insulation. And then you have transportation via the blood and blood products. I don't know why I stopped there. So fat also is connective tissue. We call it adipose tissue. You are supposed to have a percentage of fat. Now I don't know what it is, but you are supposed to have a percentage of fat in the human body because you need it for neuron axon connections and other vital life processes. But then you're not supposed to have as much fat as, say, Miss Mills Moore has, because that means that you are not utilizing the energy that you are consuming, and so your body is storing it, which is unnecessary. Because we don't, well, typically I would say we would not ever come across a time where I would be starving, but with the world going the way it is, maybe I'm wrong. Connective tissue characteristics, they all have a common origin. When you are formed in the fallopian tube, when sperm meets egg, you're just a couple of cells at the beginning, and then you multiply and you multiply and you multiply. And actually what happens is you invert and you become a hollow ball. So the center is hollow, and then you have the cells on the outside. And either very shortly before that blastula implants into the uterus or very shortly after, the blastula actually has already separated into 3 layers of cells around that hollow ball. And those cells are called the endoderm, the mesoderm, and the ectoderm. This is important. And in fact, there's a couple more slides that reference tissue development in utero. All connective tissue comes from the mesenchyme, which is embryonic tissue that comes from that middle mesoderm layer. So it's all from the middle layer of the blastula, which once it's implanted is called an embryo. So there are degrees of vascularity. Cartilage in your nose and in your sternum and in some of your joints is avascular. So you will find that if you damage your cartilage, like in your knee, It very, very slowly can heal itself. But the reason it's not quick at healing is because it doesn't have a blood supply to it. So we'll find out in inflammation processes that blood carries, you know, the good things to you and the bad things away from you in terms of inflammation. When you're not avascularized, you have a hard time healing. And something about the nervous system too, but we're not there yet. Dense connective tissue is poorly vascularized, and obviously blood is highly vascularized, right? Okay, before we get into specific types of cartilage, they all have things in common. They all form a matrix. Okay, well, let me just, what is a matrix? It's a non-living substance that that surrounds living cells. So, but it includes ground substance that can either be fluid like plasma and blood, or it can be super hard like cartilage tissue. And then it also includes fibers, collagen, elastin, or reticular fibers are what they call it. And we're gonna learn what each of those are. So you have a foundation basically called a ground substance that's either going to be fluid or hard or somewhere in the middle depending on what the tissue does. And in this ground substance are going to be cells and fibers. And that ground substance is called a matrix. The matrix is important because it's able to bear weight like bone can, and some cartilage. It can withstand great tension like bone, and endure abuses such as physical trauma or abrasion, which is road rash or rug rash when you rub up against something and it takes away the skin layer, and then you have that collagen layer. The three main components of connective tissue are ground substance. We just talked about it. It's either fluid or hard or somewhere in the middle. The fibers, which are either collagen, elastin, reticular, or all three, or a mixture of the three. And then the cells that live in that tissue. For example, in bone, your cells are osteocytes. In blood, your cells are the red blood cells and the white blood cells and the cells of the immune system. And other cartilage, they have specific cells, and we're going to see those. The ground substance and the fibers make up the matrix. The cells are the living organisms that are being either fixed in the matrix or that travel through the matrix, depending on which cartilage tissue we're talking about. Okay, so your ground substance is amorphous, which means that it doesn't really have a structure. Even if it's cartilage, it kind of just filled in that space between the cells and the fibers and then hardened, but there's cells in there that are alive. It can be made up of all the following stuff: interstitial fluid, so fluid from between the cells, glycoproteins, glycosaminoglycans, that coil up and intertwine and trap water, forming fluid to a semi-stiff gel. Now, when you see pictures of cartilaginous tissue on slides, what you're going to see is something that's been fixed into place. So it looks like everything is solid, but it's not. Like, for example, you'll see dried blood on a slide, but we know that blood is fluid. And then the semi-stiff gel that they are referring to is like the layer under your skin, the basal lamina and the collagen layer under there. It's, you know, you can push it around, and that's semi-stiff. It's gelatinous, in other words. Ground substance will function as a sieve to allow nutrients and other substances to diffuse between the cells. Those three fibers, collagen, elastin, and reticular. So collagen is extremely tough and provides high tensile strength. There are women in this world, and men, of course, who don't ever wrinkle in their faces. They have high levels of collagen that doesn't break down over time. That's not the only thing that stops you from wrinkling, but it does help. It forms collagen, right? Often called white fibers because of its glistening white appearance. If you are a cook or if you have ever helped in the kitchen, your parents prepare meat, be it chicken or pork or beef, you might find little tough pieces in the meat that are white. And if you pull it, you kind of just pull out the string of what is actually collagen, and then you throw it away so that it's not in the meat and it's easier to eat. Elastic, which it's just elastin, it forms the protein elastin. Whoops, back. And it's coiled like a rubber band, and it stretches and can recoil just like a rubber band. And you can read that example. They're found in areas with great elasticity, such as the skin, the lungs, and blood vessel walls. And it's often called yellow fibers due to yellow appearance, which I guess I've never heard of before this exact moment, and so neither have you. Then you have reticular fibers, and they are fine collagen fibers. So they're very thin compared to collagen and elastin fibers. They branch extensively, forming a net in their ground substance and around their matrix. It's a fine mesh around which small blood vessels can flow through. It supports soft tissue of organs and found at the junction between connective tissue and other tissue types. So that's where you find it. The cells then in all of our cartilaginous tissue, of course, depends on which tissue we're talking about. In proper connective tissue, the cell is called a fibroblast. In cartilage, it's called a chondroblast. Now, blast actually means immature cell, so this would really be a fibrocyte and a chondrocyte when they're mature. In bone, it's an osteoblast, which would turn into an osteocyte. In blood. In blood, it's a hemocytoblast, always actively mitotic. And what this means is that this immature cell is always actively producing other cells, which will then be triggered to become mature white blood cells, mature red blood cells, and or platelets. Right, so each cell type exists in immature and mature forms. The immature form is blast. Whoop, sorry, I thought there was another line. And the mature form is cyte. So everything that is a blast up here, you can also put another arrow and then write fibrocyte, chondrocyte, osteocyte, just hemocyte, there. Macrophages exist in most cartilaginous tissue. They're large, irregularly shaped cells that avidly phagocytize both foreign matter that has invaded the body and dead or dying cells. They're the ones that do phagocytosis. They go around and eat everything. They're the first line in your immune system. They can trigger the rest of the immune system if necessary to do a whole immune response. There are cleaners of our body system. Macrophages may be loose and migrate freely, or they may be stuck in a structure like bone or dense cartilage, and they don't get to migrate. And then depending on who found which macrophage, they actually have different names. So you have histiocytes, which I've never seen that before in my life, and I think it's spelled wrong, is loose connective tissue. Kupffer cells is a real thing, and it's in the brain. No, it's in the liver. And they're macrophages. They're the same thing, but they were found by Dr. Kupffer, and they're in the liver. And then microglial cells are macrophages in the brain. So all classes of connective tissue consists of living cells surrounded by a matrix. We have discussed that. Major differences reflect cell type, fiber type, and proportion of the matrix contributed by the fibers, which means whether it's a dense matrix or a loose matrix. So once again, you have dense and loose connective tissue proper, cartilage, bone, and blood. And in 3 slides, we'll start to get to see how those are all different. Nope. Just like with the epithelial tissue, they all have different names. And so you'll have to learn the different names. This one is not as nice as simple or stratified and then the same names over again. So it's a little bit more memorization. This is just extra information about embryonic tissue. We already talked about how all this connective tissue comes from the mesoderm, which is mesenchymal tissue. all the mesenchyme makes the connective tissue, and that arises from the mesoderm. And then specifically in the embryo, and then also the fetus, we have a type of mucous connective tissue called Wharton's jelly, which supports the umbilical cord. And that is not necessary information, this slide. These are necessary information. So we're going to talk about connective tissue proper. Remember, and then you have cartilage, bone, and blood. This is connective tissue proper, and it comes in these 6 different versions. 3 are loose ground substance matrix or loose matrix, and 3 are a dense matrix. You have areolar. It packages the organs and it surrounds capillaries. You have adipose, so it's fat. It's for insulation, support, and protection. And then you have reticular, which is a soft internal skeleton to support other cell types. And we're going to have individual slides for each of these. Then if you go into the denser matrix, you have dense regular. It attaches muscles to bone or bone to bone. These are our tendons and our ligaments. Dense irregular provides structural strength, and this is the layer under our skin. And then elastic, which provides durability with stretch, like a good pair of jeans. Don't write on this slide. Okay. Okay, areolar. Here's what areolar looks like. This is what it would look like on the slide. You can see these very thick collagen bands. You can see the very, very fine reticular bands. And in the middle, specifically, you have this middle-sized elastic band here. So areolar connective tissue contains all of the fiber types. This is the most widely distributed connective tissue in the human body. It's soft and pliable. It soaks up excess fluids. It wraps organs and holds them in position. So here is mucosa epithelium. It could be in the respiratory system, the digestive system, the urogenital system. We talked about all those being mucosa tissue. And then here is what is called the lamina propria, which would be your areolar connective tissue. And it is for support and holds things in position. So all 3 fiber types in a loose matrix. And then here you see the fibrocytes or the fibroblasts, which look like black-eyed peas in this picture. But then you have adipose. Adipose is fat. Adipose is a relatively easy slide because when you look at it, it's going to be very hard to see anything. And that really is because in an adipose cell, it is so full of fat, it actually squishes the nucleus and all the cell organelles along the edge of the cell membrane, and you can really hardly see them. If they're not, well, fat doesn't stain also, and so you might be able to see the outline of the cells, but you won't really get to see the innards of a cell like you're used to. So adipose is an areolar tissue, but forget that word. This is just adipose tissue in which fat cells predominate. It insulates the body. It protects the organs. Serves as a site of full storage. Women, we have hips and breasts. We have those curves to our body specifically for reproduction purposes. The breasts, as we know, as women, are just fat deposits on our chests that also support mammary glands if they are ever engaged to do that. Reticular connective tissue. We're showing you the spleen right here. It forms a supporting framework for lymph node organs. Sorry, my mouth. So lymph nodes, spleen, and bone marrow. It is a delicate network of interwoven fibers. And so you have those very, very thin reticular fibers running through here. And you have reticular fibers. And it should have fibroblasts in here, but it's mostly focused on the fact that there's blood cells running through it because the spleen filters the blood and gets rid of the old and dying red blood cells and et cetera, spleen functions. You'll learn more about that in the spring. Our tendons and our ligaments are dense connective tissue. This one's fairly easy to recognize in a slide. It looks almost identical to this picture that you're seeing here. It's wavy, densely packed fibers, and these are all collagen fibers with these fibroblasts squeezed in between the fibers. And it has, you know, a structure to it. It has directionality. It's not all over the place like that areolar tissue is. Tendons, muscle to bone, and ligaments are bone to bone. Cartilage, before we get to the picture to show you the slide, cartilage stands up to both tension and compression. So it's flexible enough to not snap like a bone could. And that flexibility, it says, is a characteristic of dense connective tissue and bone. It's avascular. You can severely damage some cartilage in your body, and then it's not ever really gonna heal back to 100%. It will eventually heal to probably functionality, but sports injuries, really bad sports injuries, it'll end careers and other things when you damage the cartilage. Made up of almost 80% water. It can rebound after being compressed, and you have chondroblasts and chondrocytes for the cartilaginous cells. So it doesn't even look like it has a matrix back here, but it's actually a hard matrix, and these cells cannot move around within this matrix. They are stuck in these little holes that are called lacunae. This is hyaline cartilage along our rib cage here. And the most common and abundant cartilage supports and reinforces resilient cushioning properties like a pillow. No, not like a pillow, but it cushions your delicate organs and resists compressive stress. Now, as we know, when you're doing CPR, you can actually break those pieces of cartilage. You can break the ribs, so it doesn't resist 100% of stress, but it does have the ability to recoil, right, in CPR, to compress and recoil, and it does do the protective functions that it's supposed to. Your entire fetal skeleton starts out as hyaline cartilage, but some of it does start to ossify before you are born. In very certain areas of the body, the hyaline cartilage remains until you finish growing, which typically you finish growing at 21 for females, 25 for males, but you really slow down growing the second you hit puberty. So that mass release of hormones with puberty, specifically for females, kind of actually stunts our growth, and that's when you really stop growing. Males, I think the testosterone actually puts you into your growth phase, and y'all shoot up like you were 3 feet tall, and all of a sudden you're 6 feet tall. And then y'all stop really growing at about 25. At the end of our long bones, our femurs, our humeruses, radius, ulna, tibia, and fibula, you have these things called epiphyseal plates. And those are areas of hyaline cartilage that actively remain mitotic so that your bones can grow as you go through your growth phases. And it covers the end of long bones as articular cartilage. And that's what I keep meaning when I say that you can have career-ending sports injuries. You can injure this cartilage really bad. 3 varieties of cartilage continue. Number 2 is elastic cartilage. Elastic. It maintains its shape while allowing great flexibility. Your ear is elastic. The outer edge of your ear is elastic cartilage. It contains more elastin fiber than hyaline cartilage does, and located in areas where strength and exceptional stretchability are needed. External ear and the epiglottis. What did I just do? So you can see it's not as finely packed as the hyaline cartilage. It is still structured though. Once again, these cells are not moving around the cartilage like they could in areolar tissue. They are stuck in their lacunae. And you can see the collagen fibers are rather dense in that matrix, which makes it more of a solid. And then there's elastin fibers as well. to give it its elasticity. And so it's showing you here, we said the ear, external ear, and epiglottis, and then here it's showing you the intervertebral discs. Try saying that 3 times fast, of the spine. So it's highly compressible and resists tension, found wherever hyaline cartilage meets a true ligament or tendon, where strong support and ability to withstand heavy pressure are required. Forms cushion-like discs between vertebrae, and it is the spongy cartilage of the knee. Bone is easy. This is what bone looks like under a microscope. It looks exactly like this. It is used to protect the body and support the body. It provides cavities for fat storage. In the long bones, I told you, I think already, maybe that was biology, but as you grow, your long bones as a child are full of red marrow, which is supporting red blood cells. But when you have stopped growing, the red marrow in long bones turns into yellow marrow, and it's a site of fat deposits. So it provides cavities for fat storage and synthesis of blood cells. So you have your blood cells, your bones, your osteocytes are still in lacunae, and they're these little black spludges that are going around this structure here. They're stuck in these little lacunae. A hard mixture of matrix of calcium salts, right, because bone is made of calcium, and large number of collagen fibers. Because of the calcium salts and the lacunae, bone is much more rigid. This whole thing, this whole structure, each circle, like a circle in a tree, if you cut a tree down, it's called a Haversian canal. And in the center here will be where the blood supply is going to feed those surrounding cells. And here's a blood supply, and here's a blood supply. And then the cells can communicate with each other through these little squiggly lines you see, which have a very specific name also, and I have to remember it. So the osteoblasts, the immature bone cells, build the bone. They produce the organic portion of the matrix. Blasts build the bone, and when the bone is built, those blasts are stuck where they were, and they turn into osteocytes. They mature, and they're found in the lacunae. Bone is very well supplied with blood vessels because there's no earthly way that the osteocytes can get nutrients to them or waste away from them without a bone supply running through those hard calcium salts. Then you got blood. Blood is a connective tissue. People don't think of it that way. Blood doesn't just automatically exist in an embryo / fetus. It has to actually be formed. And then the fetus gets its own blood supply. So it's atypical because it's a fluid, and nothing is bound anywhere. There's no elastic anything running through it, or no fibers running through it. It's a loose fluid with cells. Definitely doesn't give mechanical support. Its whole point is transportation, as you know, of nutrients and wastes. It is classified as a connective tissue because it develops from that mesenchyme and consists of blood cells surrounded by a non-living fluid matrix called the blood plasma. And these are red blood cells, and these are macrophages, or neutrophils. This is a B cell or a T cell. They do look different. The fibers that you don't see running through the blood, they're actually soluble protein, and they're visible only in clotting. And we know the reason for it. We know the functions. You know the functions of blood. But if you don't, they're right there. And then here is a magic school bus video. Let's see if it actually opens. Okay, well, not while I'm sharing it, but I'll see if it opens when I'm not, and if it can be shown. Love the magic school bus. I have been called Miss Frizzle. I wish. She's so much fun. Oh my, so that was the end of connective tissue. How long have we been doing this? I have no idea how long we have been recording. Possibly about 30 minutes. I have no idea when I started either, but I'm gonna keep going because we need to finish this PowerPoint. So back to sharing. Still recording? Good. Nervous tissue, your third primary tissue type. It actually comes from probably going to say the wrong one. So let me wait until the slide tells me. But it comes from a different tissue layer than the connective tissues in the embryo. It's found in the brain, spinal cord, and nerves, right? Functions and regulation and control of body functions. It is a neuron. This is the dendrite of the neuron, the little center structure that has, well, these are the dendrites, I'm sorry, the small projections are dendrites. The center structure is where the nucleus and organelles are, and if you have a very long structure coming off of it, it's called an axon. And dendrites receive impulses, axons transmit impulses. The neuron is highly specialized nerve cells that generate and conduct nerve impulses. There's other supporting cells in the body. Oh, I'm sorry, let me finish the neuron. The neuron is a branching cell, like I showed you. It has the dendrites that are smaller branches, dendritic in reference to trees in Latin. And then the axon can be a very long branch coming off of it. The presence of these cytoplasmic extensions allow them to transmit the electrical impulses over distances in the body. There's actually a lot of supporting cells in nervous tissue that you might have never noticed or known of before. And they're cells that support, insulate, and protect the delicate neurons. Your myelin sheath, this is one of the reasons that you have to have fat in your body because it insulates long nerve fibers and increases the transmission rate of nerve impulses. There are genetic disorders, should name the know of it. It's either Lou Gehrig's or it's something very similar, where the myelin sheaths are systematically destroyed and you start to lose control of your body. Like it starts out with tremors, and then you start tripping over things, and then you have shakes and tremors, and then you can no longer control your body movement, and it eventually leads to, you know, coma and death because your brain can't transmit impulses to the body. So the myelin sheath is very important. Oh, that was apparently it for neurons. So let's go to, well, that's because that's all it is. It's just the neuron. What do you need to know? Muscle tissue. Hopefully you know you have 3 types of muscle tissue. You have cardiac, skeletal, and smooth. Oh, good, I remembered them all. Muscle tissue. These are highly cellular and very well vascularized tissue because it takes so much energy to power our muscles. They have to have a ton of oxygen supplied to them because remember, we do cellular respiration and you need oxygen as the end stage product. When we are working out super hard, we put ourselves in an anaerobic state, and then we create lactic acid, which will build up in your muscles and cause cramps and everything. And if you are really into working out, you've probably already experienced that. Muscle tissue's function is to produce body movements, also to keep us warm, also a layer of protection as well. They are composed of myofilaments, actin and myosin. One of the most favorite things that I like to teach, because it was one of my favorite things to learn, is specifically how the actin and myosin function. And so we're going to get through tissues and integument system. Then we're going to do skeleton system. Then we get to the muscles, and you get to learn all about how the actin and myosin work together to contract a muscle. See? They work together to bring about contraction of muscles. It wasn't crazy. Skeletal tissue is highly organized. They have these Z bands or I bands. They're packaged by connective tissue. They form the flesh of the body, which means if we were to be the type of organisms that eat other things, which I guess we were. So when you eat chicken and you eat beef and pork, what you're eating is the flesh of the body. You're eating the muscle of that animal. As they contract, they pull on bones or skin. Whoa, sorry. Whoa, what's happening? Nope. Causing body movements. We can control it voluntarily, like me scratching my eyebrow just now. That was not intentional, but it was happening. Or we can it's involuntary, like the blinking of an eye. Trying to think of other involuntary movements. I can't really right now. Blinking's one of the main ones. The cells are very long and cylindrical, and they are striated. So that's what I wanted to say about the Z bands here and these I bands. They literally, you can see these stripes or striations in the slide. And so they're typically very easy to recognize. They also are multinuclear cells because of how much it takes to organize and produce them, so multiple nuclei per cell. Smooth muscle, what the heck? Does not have striations. It's also not this loosely packed either. It's more dense than this. But you'll just have single cells, elongated cells with a single nucleus. This is our involuntary muscle. It's what moves our intestines, and it's what moves all of our organs, basically, and allows them to do functions. The individual cells are spindle-shaped and contain one centrally located nucleus. Walls of hollow organs, except for the heart, because the heart is cardiac skeleton muscle. No, cardiac muscle tissue, sorry. Digestive and urinary tract organs, uterus, and blood vessels. And they function by squeezing substance through. They squeeze, relax, squeeze, relax, squeeze, relax. That is called peristalsis. Cardiac muscle, found only in the walls of the heart, function as the pump blood. They are striated like skeletal muscle, but they are branched. They have branches like this, and then they have this thing called these intercalated discs that run through them. So, and you can definitely see that in a microscopic slide. And it's one nucleus per cell. So like, but different. Skeletal muscle is under our control. We often call it voluntary, but cardiac and smooth muscle are involuntary. We don't tell our heart to pump. The final section of this PowerPoint, we are very nearly done, good for us, is tissue repair or wound healing. Most of our tissues can repair themselves, blessed be, because if not, we would die very quickly on this planet because we would just rub everything away or break it, and that would be the end of us if they didn't repair. You have mechanical barriers to protect us, skin and mucosa, and that ciliary action I talked about in the respiratory and the digestive tracts, the last PowerPoint. And then chemical barriers like stomach acid and sweat on our skin. If the barriers are penetrated, the body initiates inflammatory and immune responses, mainly within the connective tissues. We try not to let things get past those first lines of defense, though. The inflammatory response is non-specific. All it knows is that an injury has occurred. It doesn't care what the injury is. You can sprain an ankle, you can puncture something through your skin by accident, step on a nail, you can stub your toe, you can jam your finger in a door. It doesn't care what the injury is, it's going to respond to it. So it develops quickly and occurs whenever or wherever tissues are injured. Reasons for it. Inflammation is characterized by redness, heat, pain, and swelling. Those are the 4 characters of inflammation. And it all has to do with increased vascular activity. I don't know why I'm pretending like this is inflamed. Increased vascular activity at the site of injury. So the very first thing that happens when you get injured, and maybe the next slide says all this, but the purpose is to get a whole bunch of blood flow to there to get rid of the harmful agent and prevent further injury and restore the tissue to a healthy condition. Because with blood flow comes platelets if you need clotting, comes immune cells if you need an immune response, and increased oxygenation and nutrients. Inflammation is non-specific. Immune response is extremely specific. So let me go back. Heat, redness, pain, and swelling. Heat and redness come from the increased vascular permeability. So not only do the blood vessels expand in your site of injury, let's say I've hurt this knuckle here, but they also become leaky, what's the technical term, so that cells can move out of the blood vessels into the surrounding tissues. When you have leakage into the tissues, it's going to cause compression of the surrounding nerves, which that's why you get pain. And the swelling is due to the damage, but also to the increased vascular permeability. Okay, the immune response is extremely specific. We learn about it in the spring semester right as we start talking about the cardiovascular system, and it takes longer to activate. You have so many different types of immune cells running through your body. all on defense to protect you. And you have ones that are called memory B cells that are waiting to come in contact with something you have already mounted an immune response against. And you should never know that you've been infected with that same organism twice, because your memory B cells just take care of it. But if you are infected with a new organism for the first time, you have to mount that entire immune response over again. And so that happens by your natural macrophages, be they microglia cells, Kupfner cells, histiocytes, whatever. They eat something and they will find out, they display the protein of whatever they ate on the surface of their cell. And they will go along to another immune cell, a B cell, and be like, hey, look, here's a protein. Have you seen this protein before? And the B cell will either say, yes, we have, and then you just don't worry about it. Or the B cell will sound the alarm that no, I'm sorry, I'm choking. They have never seen this protein before. And they take that protein and run it to a lymph node. And they're like, here's a brand new protein. We have to mount a response to it. And so your lymph node, be it the ones in your neck, your armpit, your groin, whatever, they get all inflamed because they are mounting that response. They are activating all the T cells, and well, B cells in the lymphocyte to go out and start attacking. At the same time, your B cells are activating your T cells. And what your T cells do, T4 and T8, they go up to cells that have already been infected by this new organism, and they cause cell death, so that the new virus, bacteria, whatever, can't create more of itself within the cell if the cell is dead. And so that's how the immune response works, and then antibodies are produced. Tissue repair, cells need to divide and crawl to the site of injury. And this is done by, whenever you have an injury, you have things called cytotoxins released immediately into the surroundings, and they're also referred to as cytokines. And this causes chemotaxis of specific body cells to come to that area. Regeneration, we replace the destroyed tissue. And then we can also get scars from fibrous connective tissue actually kind of overproducing itself. So these are the two things. You can regenerate and not have a scar, or you can have a scar. What occurs will depend on the type of injury and the type of tissue damaged. The 3 steps to repair are: inflammation has to happen first. You got to get all those cells in that blood to the site of the injury. If you've like sliced a deep chunk of yourself, then that has to heal up, and in that area that you cut open, you have to restore the blood supply through that area. And so then you can get a clot, and as the clot is exposed to air, it forms a scab, and then underneath the scab, granulation tissue forms. And as the granulation tissue hardens into new tissue blood supply, new blood vessels are put through it. Sorry, like 2 slides left and I can't hold it together. And then regeneration, either restoring the original skin or creating a scar, results in permanent repair. Tissues that regenerate easily, skin tissue, we know that, and fibrous connective tissue and bone, because they're highly vascularized. Tissues that regenerate poorly, skeletal muscle, and tissues that are mostly replaced with scar tissue are cardiac muscle and nervous tissue. Nervous tissue doesn't typically heal. So paralysis victims, hemiparesis, or a hemiplegic, quadriplegic, whatever, paraplegic, that's the 3rd one. They're typically stuck with their injury for life because nervous tissue is not vascularized. These are the 3 layers. And the embryo, as it's being formed, ectoderm being the outside layer, mesoderm being that middle layer we talked about with all the connective tissue, and then endoderm, and they form these tissues. So epithelial tissue comes from all 3 germ layers, because you have epithelial tissue in all layers of the human body. Muscle and connective tissue, mostly from the mesoderm, and nervous tissue from the ectoderm. I'm sorry, I didn't mean to stop sharing. And then you had a final essential question. How do the 4 basic types of tissues in the human body contribute to homeostasis. Well, they protect, they support, they provide communication among cells, and they help resistance to disease. So that is the tissues PowerPoint. Before Monday, I will then post the integumentary system PowerPoint. And so I will see you in class. Thank you so much.